Morning, so let's continue with things related to reduced models. So last class, we saw things about plane with exchanging derivatives, right? Like up to a certain order of the model, we can exchange a time derivative for a spatial derivative. And that was done, for example, when one looked at the KdV and the BBM. So the KdV, I guess I should say the linear KdV, is like this. And the linear, excuse me, BBM is like this, right? Which at first is a minor change within the asymptotic hypothesis we've made. Actually, many times write it like this, doesn't matter, right? Which we see that we can exchange for this problem if we had an epsilon here, which is how we deduce this model, okay? We can exchange a time derivative for a spatial derivative for a time derivative, and it changes the sign. Okay? So the dispersion relation for the KdV is this. It's called a dispersion relation. Right? I'm going to show to you dispersion relations, numerical dispersion relation. So today this course is not a course in numerical PDEs, right? I won't give you any homework of numerical PDEs or anything, but today's class is going to be on numerical differential equations, most of it, because I think it's interesting to at least, right, to expose to you, have this on video and so on, some facts that I think are fun. So the dispersion relation of the KdV is this. The dispersion relation of the BBM is this, okay, which to leading order, right, will look like, no, do I have this right? Yeah, I think so. Which to leading order is like the BBM. Okay. So you can double check this. That's right. This guy comes over here, and this fact can influence things numerically, right? As I mentioned last time, high frequencies of the Fourier representation of the long wave solution, right, will have different numerical properties. In some cases, actually, we can get instabilities and so on. I also mentioned that these equations have solitary waves. For the nonlinear KdV, the solitary wave is a soliton. For the BBM, it is not a soliton in terms of collisions and so on. Okay. Now, let's leave this at here. Sorry. And let me just call the attention to, remind you that this is a Padé approximation to the full dispersion relation. And this is a polynomial truncation of that hyperbolic tangent, blah, blah, blah. If you go to one direction, this is a Padé approximation. It's a rational approximation. Okay? Now let's switch channels. I like this. This is fun. That's why I decided to ODEs, to very simple ODEs. Okay? Now let's do a little bit of numerical ODEs, and then I'll do numerical PDEs, and I will come back, you will see how, to something that reminds us of the linear KdV equation. So bear with me and we'll see this. So if I'm doing a numerical ODE, right, and I have this problem. Just abbreviate it like this, diagonalizable, okay? This is a linear problem. Constant coefficients. Okay, let me put it here, not, which means, right, the matrix is constant. And related to this problem, in numerics, we have the following problem that's called a test problem that leads to the notion of absolute stability. Okay? So the test problem is this. Look how simple the problem is, okay? Here I'm thinking about systems, okay? Here I'm looking at the scalar trivial case, right, that we know the solution. This leads to a solution super simple. So why is this a test problem? And these are, when I give the numerical PDEs course, I basically start with numerical ODs to set the tone, to set language, to set concepts, and so on. And this is a little bit what I'm going to show you is an elementary. I think it's an undergraduate. I mean, it's really an undergraduate problem. It doesn't appear everywhere. Very simple. So why is this the test problem? At least in my understanding, in informal, colloquial way. This is like, and I'm talking about stability. So I always say you build a new car, a new bicycle, a new whatever. You want to test it first in a simple environment, right? You don't get the car and you go to the street, you test it in an oval track or whatever, something simple to test. For example, the stability of the car in curves and so on, right? Of course, stability here is in another sense. So we invent a new numerical method. We want to test it in a problem. We know the solution in a problem that is well behaved. So the test problem, in my way of sort of selling it to you, right? It's not, I didn't invent it. It's a standard thing in numerical analysis. You take a lambda, which is complex, but has negative real part. Why? So that you know that the solution decays in time. It might oscillate, doesn't matter, but it decays in time. So you know that if your numerical method generates a solution, an approximate solution, that grows in time, that is obviously what? A numerical instability. Because the solution, the true solution, you know the exact solution should decay in time. That's why it's called the test problem. And what does this look like? Right? This lambda looks like, say, could be an eigenvalue of this matrix, which is diagonalizable, which is simple, right? You can sort of use the eigenvectors. I think I indicated this at some point in the course. And you can diagonalize and uncouple this system. So therefore, looking at this problem, right, somehow you're understanding how this linear system of ODEs will behave if you take it to the computer. Okay? So this is the first problem for us to find. So with this, on the test problem, we will look. Let me put it, what is our goal? We will look for regions of absolute stability of different numerical methods. As you will see, it's very, very simple. So let me go, maybe it's best to go to the next blackboard, and I'm going to bring 3 super simple numerical methods. Okay, super simple. Then we do it by Taylor series expansion. And I put here explicit Euler, implicit Euler, and trapezoidal rule, right? You can make all these methods basic by Taylor series expansion. The first one is basic. I mean, it's all very simple. The first one is basically almost finished. It's calculus, right? I mean, all of them are. The first two in particular of approximating a derivative. Okay. So the second one, and the third one, okay, so I'm simplifying these guys. This is Fn plus 1, F1, where actually these are the methods. Okay, the notation here is for the scalar general nonlinear ODE, right? So this is Euler for this nonlinear ODE scalar. This is forward Euler, right? This is backward Euler. This is the trapezoidal rule. So this is explicit, right? You just plug in the values here and you evolve in time. This is implicit. It's more complicated because now you have to use, say, a Newton's method to find the zero of this function, if you think of it. And this is also implicit, okay? Now, if I asked you, right, I don't know if you can give me the answer. It's very simple, actually, but give the answer quickly. Is that what are the properties of these three methods if I apply it to this super simple test problem where f is just lambda y? Do they all behave the same? How do I know how they behave? Have you seen this before? If yes, you would know the answer. If not, at first it looks puzzling, but it's very easy. You want to say something? Go ahead. No, yeah, it's linear. The problem is linear. The method is going to be linear, right? So look, let's do it here. This method is going to be this. This method is going to be this. This method is going to be this. Okay? Because the ODE is linear, the Newton method I had to do here to sort of find the zero of this sort of combined function, right? Why am I saying the zero? Because I can pile all this together to the right-hand side, so the whole junk is going to be equal to 0. That's like finding the zero of a function, which is this plus this, blah, blah, blah. This is already known. This is a constant, right? And here I would have to find the zero of a slightly different function. But because the ODE is linear, there's no need to do a Newton's method. Look, for example, here. I just pull this guy here over here, divide, blah, blah, blah. I know its value. Okay? Fine? Everybody with me? Good? But now, looking at this, okay, I'm going to do now, this is for the test problem. This is for a general problem. This is for the test problem. Now this, I find this very cool because it's so simple. I mean, you can teach this to first-year calculus students, and maybe not everybody sees this in a numerical differential equations course, I mean, in this way. And actually then violating the hypothesis in a good way, violating this hypothesis that the eigenvalue, this lambda here, eigenvalue y, because I'm already thinking of this, has real part negative. I'm going to violate this and say, forget, let's let the real part be anything we want. That's what I mean by violate. But let's first start with the negative real part. So look, now, this is like a discrete dynamical system. Very simple. And these three guys trying to solve the same problem has different properties. How can we understand these properties? Very simple. It's just like writing, as I mentioned sometimes, just with a notation, writing the thing in the right way, it's super simple. So look, since I'm allowing lambda to be complex with negative real part, who cares now? Call this guy here z. Right? So I'm defining now z to be lambda delta t. Complex. Who cares? Okay? So this becomes lambda y plus 1 is equal to 1 plus c lambda 1. This is like, say, the propagator, the guy that discretely evolves this guy. This one here is going to be y equal plus 1 is equal to 1 over 1 minus z yn. This is like now the other propagator. It's different. Okay? And this one here, let's see if I do the calculations right. It's going to be 1 minus. So help me if I do it wrong. This is the propagator. Okay? Simple, right? I mean, we can learn this, teach this to an undergraduate, right? Okay, now, what do I have to ask these guys so that I can think about absolute stability? Well, absolute stability here, say absolute stability means that I want the test problem to be stable when the solution is decaying. Namely, the real part of lambda is negative, right? If the real part of lambda is negative, it might oscillate, but it decays in time. Well, so therefore, for my numerical method to be stable, I need the condition that this be less than 1. Because I forgot one thing. Let me do it. One thing that I forgot is that this is the same as putting an n0 here and doing this, okay? Doing this, sorry. And doing this. Basically by applying the method, right? I mean, coming back, right? So this is sort of the exact numerical solution for this very simple problem, discrete in time. And for this guy not to grow, the condition is that the absolute value of this has to be smaller than 1. Right? The condition here, so this is actually called condition, let me put it here, on the, and as we know in mathematics, sometimes there's this abuse of words. It's not quite an abuse, that the amplification factor has to be smaller than 1. So it's not really an amplification factor, it's a contraction factor, but it's called an amplification factor, right? If the amplification factor is greater than 1, it amplifies. If it's smaller than 1, okay? So this is the amplification factor. So the condition here for this guy, for the explicit or implicit Euler, is that z minus 1 is greater than 1. Okay? And I'll leave that the other one, so just to save space, right? We need that the whole guy be less than 1. Okay? Now, look at this. this in the complex plane, so this is in the complex, this is in the z-plane. What is this region? This is a disk centered at -1. This is the region of absolute stability. This is z minus -1. Right? So it's this disk. This is the region of absolute stability, right? Region of absolute stability for the explicit Euler's method. So that means if you have, you see, so remember that z, it's here, right? But let me write it here again. Z is lambda delta t. So if you have a negative z, so think that you have something that decays very fast, like the real part of the eigenvalue is -1,000, which means something decays very fast. So -1,000 means that it's way out here. So you have to use a very small time step, delta t, so that you put it inside the circle and then it will decay. Or else it will actually grow numerically. Can you see that? Right? If you're you know, there's some problems that there is something that decays very fast, and sometimes, for example, in numerical chemical problems, the reaction is very fast, so the concentration of something decays very fast, right? So if the decay rate is -1,000, you need a very small time step so that the z is in here, is inside this disk. Or else your numerical solution will grow when the exact solution decays. Okay, do you follow me? So this is, you know, it's a numerical method, but it's like a discrete dynamical system that you have to keep it. This is its stability region. Okay? All right. Now this implicit one, look what happens now. And look, this is just a very simple Taylor series, one going forward and the other one going backwards. Very simple Taylor series, very, very simple. Now, now this one, it's saying that this is the condition. A disk centered at 1 okay? But what is the region of stability for this disk? It's outside. Cool, huh? It's the opposite. It's outside. This is the region of absolute stability. Okay? So, for the test problem, because in the test problem, lambda is negative, it's somewhere around here, so it's in the, let me highlight this, it's in the left right plane, just to highlight, for the test problem, this method is unconditionally stable. No matter what delta t I use, it's always going to be here. It's stable. So for the problem that decays very fast, with lambda -1,000, it's not going to go unstable. It's not going to grow. You know, if I use a big delta t, I'm going to get a very bad solution because I'm trying to, with a big time step, see something that's decaying very fast. I'm going to see a very poor solution in terms of accuracy. But it's not going to go unstable. You see the difference? Right? Because it's in the region where the amplification factor, this guy, is smaller than 1. So it will decay in discrete time. Okay? Now, if we do the region of absolute stability for the trapezoid rule, it is exactly the left-right plane. And look, for those who know complex variables and things like that, these will look a little bit like right, regions, like this is a region. This looks like a linear fractional transformation of the disk onto a half plane and so on, right? But anyway, there's many ways to show this. So this is like the border of this region, or this, right, infinite radius disk. So you see, we have three very similar looking methods. This one looks a little bit like the average of the other two, right? It's the trapezoidal rule. This one actually, it's called the trapezoidal rule because you can also design it by looking at the integral equation instead of the differential equation. What does it mean, the integral equation? Is that you can write the OD like this, right? And then you do a trapezoidal rule integration of this. That's how you get that. Instead of, you can do it from the Taylor series too, but it's easier to do it like this, right? Just a trapezoid rule integration of the differential equation written in this integral form. Okay, now, look, now these are the comments, these are a few of the comments which I think is very important. That's why I wanted to show it to you. And I can see from your expressions that maybe, I don't know, maybe you haven't seen this before, right? It's simple. Don't you agree? It's very simple. I don't know, have you seen this before? No, right? But it's very simple. You can teach this to an undergraduate friend, right? Now look, other things which I think is very, very cool, maybe even more important than up to what we did now. Now it's really even the more important facts, right? So this is the test problem and its related absolute stability. Now, why do I have to still stick to this condition here? Real part of lambda smaller than 0, right? It was important. It was important because it made me draw these drawings, these regions. But now, let me relax this hypothesis, right? I have this matrix which is diagonalizable, right? If this matrix, now see if you agree with me, if this matrix is related to some oscillatory problem, like of the type of a mass spring or whatever, what are the eigenvalues of this matrix if the problem is an oscillatory problem? They are what? They could be complex conjugates, but now let's think together. If it's complex conjugate and it has a real part, that means the oscillator is decaying, which is okay. It's like a damped oscillator, harmonic oscillator. Or it could be also an oscillator that's growing in a legitimate way because it has sort of a resonance, like a periodic forcing that makes it resonate. Everybody with me, right? So if you have a complex eigenvalue, good start. Exactly. That's where I'm going to get. So I'll say it soon so that the camera gets it. So the real part of the eigenvalue, if it's negative, it means it's an oscillator which has damping. For example, let's think of a mass spring. It's an oscillator that has damping and slowly goes to 0. That's legitimate. Also, I could have a forcing, a resonant forcing, where the oscillator starts to oscillate with larger and larger amplitudes and grows in time. Also legitimate. But if I have a harmonic oscillator that just oscillates forever with no damping, whatever, it is just purely imaginary, right? The eigenvalue has 0 real part, okay? Now, I'm a salesman to you, and I have 3 numerical methods for you to solve your harmonic oscillator. What that means, there's no damping, and there's no resonant forcing, okay? I have 3 numerical methods for you to buy. You can only choose one for the harmonic oscillator. And tell me why. Please don't feel free to say something that's wrong. I mean, we're learning, right? And then if you say something wrong, I'll fix it. And maybe you might just say something right. Which method do you choose for a harmonic oscillator? Or at first you can also say which method you will not choose for sure for the harmonic oscillator. I'm giving already you a hint. There's one method I'll tell you, oh, this one, if you give it for me for free, I'll throw it in the waste basket for the harmonic oscillator. So I'm already giving you a hint. And feel free to take guesses and, say it wrong. It doesn't matter. This is also a test problem for us, right? We're practicing our knowledge. So a harmonic oscillator, I tell you, there's one method that if you say, André, you can have this method for free. You're the student and said, I don't want it. Let's start with that question. Which method? I don't want it for the harmonic oscillator. Remember that harmonic oscillator, at first we see it as a second order equation, which we can transform it into a system, right? By saying that, one guy is the first derivative of the other one, but we know how to reduce second order guys to a system. Okay? But anyway, so let's go. Let me help you, since we're already taking some time here. A harmonic oscillator has purely imaginary eigenvalues. Okay? So, okay, and I have when I teach the numerical methods course, right, I have this matrix A here. I give a little example, which is like this. Epsilon, delta, I think it's minus delta or whatever here, right? Epsilon. So like this, you can play in the complex plane without using complex numbers, right? So the case I'm asking you is delta epsilon equals to 0. Because here I think the eigenvalues are going to be epsilon plus or minus I delta. Okay? All right, so I have lambda purely imaginary. Which method I will not use? Let me help you. But you see, what I like about this is that it's very simple, but if you haven't seen it before, which I think is the cases of the audience here, it's like, you say, I don't know, what is Andrea talking about? I mean, why is he? So look at this. I will not buy, don't give it for free, I will not take it home, the explicit Euler. You know why? Because if lambda is purely imaginary, z is also purely imaginary because it's just lambda delta t. So my point is somewhere here. So always be outside the region of stability, of absolute stability. You see, here, this guy here will always be greater than 1 because this guy is only smaller than 1 in here. Actually, I'm already giving you a hint for which method to buy. I already would like a method where the absolute value of z, not the absolute value of z, but the absolute value of the amplification factor is equal to 1 because I want this guy to oscillate. You see, I want the absolute value of this guy to be like the same absolute value of the initial condition to some extent. Okay? But okay, let's do the first part of the exercise first. So if I have this guy here, no matter what I do with the delta t, it will never get in the disk. So I don't want this method. My solution is going to grow. It's going to start oscillating and growing, but it's not growing because of a resonance. It's growing because of a bad numerical method, which is unstable. So for the oscillator, for the harmonic oscillator, the Euler method, the explicit Euler method is unconditionally unstable. It will be unstable no matter what you do. Okay, let's go now to implicit Euler. Implicit Euler, I have the point here, right? The same point. What will the numerical method do? Yes, decrease. Very good. Both of you said correctly with different words. Decrease or damp the solution. Right? Decrease is correct because it's in the region where this guy here is smaller than 1. Another way, that's the correct, say, let's put it this way, since this is an applied course, this solution will decrease is the correct mathematical answer, and that it will damp is the correct physical interpretation. But hey, I had a harmonic oscillator with no damping. So where's the damping coming from? the damping is coming from the numerical method. So I call this a spurious damping, because it's a damping that is not from the physical model. It's a damping that comes from the discrete mathematical model, right? Okay, in some problems this might be okay, and if I make my delta t smaller and smaller, I will always have damping, but the damping will be weaker and weaker. Because the border of the disk is the region where this guy is equal to 1. The amplification factor is equal to 1. Now look at the trapezoid rule. What do you conclude? That for the harmonic oscillator, the trapezoid rule is the one that's the best in terms of preserving the amplitude of the oscillator forever. You do this in MATLAB, in the numerical methods course. We're not going to do it here. I tell the students actually to start also playing with MATLAB, to put this in the computer to see the theory working there. And it's so simple, right? So you put it here, you see your solution growing. You put it here, you see your solution decaying. And you put it here, for this method, you see it oscillating forever with, as the solutions should for the harmonic oscillator. Okay? Now, this is one of the, as I mentioned, the important comments I want to make. And the other one, and that's why I actually started this, the class with this and with this. I showed you last class that when we have mixed derivatives, we got the approximation. And here it's kind of cool to see that actually in numerical methods, when we have an implicit aspect, it also gives us a Padé approximation of our correct propagator. What is our correct propagator? It's here. Look, let me rewrite this like this, just for pedagogical reasons. You see what I'm doing? Or if I put here the discrete time, this is delta t, and if I do the discrete time, which is t equals to tn. So you see, what these guys are doing are they're trying to approximate this exponential propagator in a polynomial way or in a Padé approximation way. Cool. So see, it appears in many instances. Okay. All right, let's continue still with numerical comments. As I mentioned, the class today has a numerical flavor. So now, consider the Boussinesq system. Consider this Boussinesq system, which was a kind of a good one. And now the question is, how do we solve this numerically? In particular, because we have a time term here and a time term here. Okay? Well, there are many ways you can do it, right? And one way is to discretize everything in space and time, right? Another way, which is also good so that you can check stabilities and stuff like this, is to rewrite the PDE as an ODE using the method of lines. So in PDEs and PDE, make here as a fact or a note. Sometimes this appears like this in English, which is method of lines, which simply means a semi-infinite discrete let me put it this, version where we discretize in space to get an ODE in time. So think of this. If I discretize all this in space using some finite difference scheme, this will become a system of ODEs, right? And if it's a linear system or whatever of ODEs, then I can think about stability as I did before, whatever. It doesn't really matter, right? But how can I do this as a system of ODEs with this time here? And this is actually a method, right, that I learned actually as we were researching with my first student, Juan Carlos, for a numerical method for this. And there was a simple trick that we found in this paper. (1995), so the more complete reference is in the notes, where they do this nice trick. They rewrite the system as, the first equation doesn't change. Okay, and the second one is a little different, and I have to explain what's happening. Okay, so look what was done. Nothing that sort of different. This one's the same. And this one, I pass this term over here. All the other, we throw to the other side. So this we call V, see? dV dt is exactly this term plus this term. Okay? And why did we write like this? We write the system as to look like an ODE, in the sense that if I do this approximation here, and this approximation here, and this approximation here on a grid, so if I have this like this, on a spatial grid, if I do a semi-discretization in space, right? Then this looks like an ODE for eta and t, a system of ODEs. Okay? So then, the fact is, how do you recover? So if you can evolve, so evolve this. So evolve this using an ODE method, in the notes I mentioned like Runge-Kutta or predictor corrector and so on. And then, so then evolve it. So you can go from V. Let's give an example. Go from V0 to V1, okay, time 1. But then you say, hey, wait. But then, okay, so to evaluate, look how we do this. I need to evolve this. So at time 0, I know how to compute this quote-unquote vector field of this ODE because I know eta 0 and I know u 0. So I put this here, put this here, put this here, put this here, and I could do it, okay? So then, on the next time step, I need to put here eta 1, which I'm going to evolve from here, and u1. But I don't know u1. I know v1. So now this is a this method actually worked very well for us, and I think it's cool because then an elliptic problem comes in here, which is, look, now I can get U1 by solving this elliptic problem. So you see, so think that I've solved, I've made the evolution. I went from V0 to V1. I know V1, but now I need to know U1 to substitute back in. Well, to know U1, I have to solve this problem here. Which is, look, this looks like, this is an X. This looks like an elliptic problem. If I were in 2 dimensions, this would be a Laplacian minus U. So it looks like an elliptic. And this is my right-hand side. This is known. Right? But then I can sort of do a discretization for this guy. I'll have a matrix. This will give me discretely a problem like this. I solve this problem, then I have U1, and I continue evolving. So you see, very interesting how, right, the trick, this gives us back a non-local problem here, which is the elliptic problem. You solve, you evolve. And so this is, a comment, again, on numerical things, right? I'll have another comment on numerical things, which I think is interesting, maybe next class. I don't know if I have time, but at least I'll get started today. Let's see as time goes. Now, more things for us to discuss. Okay, this is a little bit, as I mentioned, this is something which is a little more like on the information cultural side, because this is not a numerical course. I'm not going to ask you to do anything numerical in this course, but I think it's good that you hear these things and you have these in the back of your mind. Okay. Now, another question. What can we say about these equations? Let me tell you which one they are. First, it's Burger's equation. Second one is this advection diffusion, and the third one is a KdV. This is Burger's. This is an advection diffusion equation. We haven't seen diffusion yet, but it's okay. And this is the KdV equation. Okay, so what can I say about these equations? So to make a little, can you, let me first throw to you the question in a very sort of imprecise way, of course. And then, of course, I'll sharpen it. Do you know what I'm thinking, what I'm trying to get at? See, epsilon with epsilon small. Okay, so if somebody puts this on the board, for me, of course, after seeing this many times, the first thing I would think, of course, because I'm already induced by this, right? And you have not been exposed to this, as I believe. So this basically is, this is an epsilon. I'm thinking about Burger's equation with two different perturbations, right? I think that you can think of. First, a diffusive perturbation, because this looks like the heat equation that we're still going to study in a little more detail. But you've seen this before. This is the heat equation, right? Or a dispersive perturbation. This is Burger's equation, and this is a dispersive perturbation. We saw the KdV first as weakly nonlinear, weakly dispersive, but I removed the epsilon from here. Okay? And as you will see, I'll repeat this here, one thing that's actually a current area of study, of research in mathematics, right? At the Newton Institute in Cambridge, you know, in the second semester, there's going to be a school on this, on dispersive shocks. This equation here relates to dispersive shocks. And I'll make an introduction, qualitative introduction, no analysis involved, of what's going on, what's the difference between these three equations. So, as I mentioned, the issue here is a shock. Okay? So, if you put Burger's, let me put it like this, leads to a shock. We've seen that, we understand it, we know it's a weak solution, we know how the shock propagates, blah, blah, blah. Now, if I put this diffusive term here, what does it do to a shock? That's a question. Okay? So let's look at this one first. And actually, you know, this actually, I mentioned this actually is the viscous Burger's equation, or even, as maybe more properly, the original Burger's equation, because he wanted to understand things that look a little bit like Navier-Stokes, like a baby version of it, right? So as I mentioned to you, and I'll repeat this, the way I learned it, I usually call this the Burger's equation and the viscous Burger's equation. But I think originally this was the Burger's equation and this was the inviscid Burger's equation. So if you're talking to somebody and the person says Burger's equation, you guys say, and it's not clear, ask if it's the viscous or right or not. Okay, so this one will regularize a shock through diffusion. And there's one example that you can do things analytically and see exactly what's going on. It's a very nice example. So let me tell it to you. So let's ask here for a traveling wave solution. So it's a very special requirement, okay? Namely, U of Xi with Xi, sorry, not U, X minus CT, right? But in a special scenario, okay, Witham does this in more generality. I'll mention this at some point, Witham, in the Witham's book. But let's ask for this simpler case, which is we ask for a traveling wave solution. That means a solution like this, okay, connecting. Now here's the special scenario, because in this special scenario we can get things analytically. And it's very good when we can get something analytically because we see what's going on with all detail, okay? So connecting a constant left state U minus to a constant right state U plus, okay, where U minus is greater than U plus. Okay, so we're asking, can you get a traveling wave solution that goes, say, if this is a gas, right, that goes from a constant density to another constant density, which is smaller? Okay, is that, you say, is that possible? Well, to check if it's possible, we have to plug in the ansatz and see if nothing wrong happens, okay? And the answer is that one gets, you can do that as an exercise. Sometimes in this course I give it as a homework. This time I won't give it as other things to give, right? Don't have to give exactly the same homework, so those who are watching can do as an exercise, is plug this in to the equation 2. You will get an ODE. You integrate the ODE. You have constants. You play with the constants, and you force it to satisfy sort of the conditions at plus and minus infinity, which is these constant states. And eventually, this is what you should get. One gets one does get a traveling wave solution. Okay, that looks like this. See if my figure, I mean, if things speak for itself, right? So for this case, for this particular case, with constant states at the end, you can connect these states through a hyperbolic tangent. Here it is. What is to me, very nice, maybe not only you get a closed form solution, but look at this. The hyperbolic tangent scales with epsilon, which is our regularizing constant here. I mean, the size of the perturbation of our term. So as epsilon goes to 0, this transition zone here transition region or transition zone sort of shrinks, right? This is a rescaling. It sort of shrinks. And this tends to be, the hyperbolic tangent becomes steeper and steeper, right? So actually the convergence of this case is a little more in the usual sense. So what this does, so this is what we say, look. If I have this, okay, this is what, so if this were a shock, a discontinuity, right, you have this is what's called a viscous shock, right? So it's a smoothing, sort of a shaving of this step discontinuity, right? You see it right here, okay? And as the epsilon goes to 0, right, this becomes steeper and steeper and so on, okay? So this is the viscous shock. Let's see if there's anything I want to say more. No, but I have to go way to the other board now to speak about the KdV. Now let's look at case 3 with the epsilon here, okay? Now we're going to see the difference between a diffusive regularization with a second derivative and a dispersive regularization of a shock with, with a higher derivative term. So let me put here, and let me start with some KdV facts, okay? KdV facts. So let's write here the KdV. So let the KdV in this form Okay, it's just, you can do many rescalings and so on using the space and time derivative. Write it in this form, which is one of the standard forms, to ask for a traveling wave solution, integrate the ODE, okay? So let and ask for a traveling wave solution. Get an ODE and integrate, okay, right? And integrate looking for a pulse-shaped solution, which is a solitary wave, right? Pulse. Shape solution. This also could be an exercise. So that case, you integrate the ODE and you look for conditions at infinity, which are constant here and constant there, right? If you're looking for a pulse-shaped solution, you're going to find your constants. Imposing what type of conditions at infinity? That it goes to 0, right? Because it's a pulse-shaped solution, okay? So shape solution to get. So let me see if I'm writing right. Let's see. Let and ask for a traveling wave solution, get an ODE, and integrate looking for a pulse-shaped solution. One gets that. The traveling wave solution has to have this form. So, right, it's a function like this. This is what we asked, right? This is the ansatz. And this is equal to this. After you solve all the conditions and you should get this. So there's other right, the conditions. I mean, you then can calculate the formula for the speed. But this is the important expression, because this says the following: the solitary wave is, as we call, secant squared, just like the BBM one also is, right? It's slightly different formula. And if I remember, I don't remember the details, but here there's one thing that's important, is that, look, the amplitude is connected to the speed. So remember last time that I mentioned the problem of a large soliton overcoming a smaller one, because this one's moved faster than this one. Okay? And also, you see, somehow the speed scales a little bit inside. Anyway, so if you put in a KdV, right, and this sometimes in the numerical course, I tell the students to do, is if you put in a KdV as initial condition, just a secant squared profile out of our heads, it will not propagate as a traveling wave. It will generate dispersion, it will generate something else. It has to be very fine-tuned, a fine-tuned secant squared, meaning with the right amplitude, so at time 0, right? With the right amplitude and the guy in here and so on, so that it is a traveling wave. Or, as we learned, so that the nonlinearity is perfectly balancing the dispersion. Right? Remember that's the way as we deduced the KdV last class and so on. Okay, so if you just put any secant squared, or if you put a Gaussian, a Gaussian looks like a secant squared, it will not propagate as a traveling wave. which is a confirmation that nonlinearity has to be perfectly balanced by dispersion so that this is a wave of translation, as Russell called it when he saw it in the channel. Okay? So, okay. Now, so as I mentioned, facts about the KdV before I mention how the KdV regularizes a shock. So I have time. I think that's basically where probably I will finish. Let's see up to where I go. Okay? So this is the first fact about the KdV. So, okay. Now, another fact about the KdV. Let me erase here so I save myself some space and do things nearby. So, consider the linear KdV. So this is a little bit so that our intuition, we're not going to see all the details. Some of the calculations are not that straightforward. So I'm going to present results without the intermediate steps. But this will give us intuition for what happens with the KdV regularizing a shock and what's a dispersive shock about and so on and so on. So consider the linear KdV in the following form. Let me put this in the form with so this KdV here is basically the linear KdV we saw before, but in a moving frame. From the physical point of view, is in a moving frame. Basically, in a moving frame, the linear guy is this. We basically remove this guy if we're in a moving frame. Okay? No big deal. Okay, so now let's try to look. And this gives us the dispersion relation like this, minus k cubed. That comes from this guy. Right? We know that the power of k's gives us the order of the x derivatives and so on. Okay, so a Fourier solution of this linear KdV would be like this, very simple. Okay, where I'm going to already put here, why? In the notes I have this, but why? Okay. So this is, remember, with the hyperbolic tangent, I said, well, it's impossible to integrate. Here it's also quite difficult to integrate too, right? I'm integrating k, an exponential of k cubed, and so on. But this leads to the following. But this can be equal to, let me write here, can be rewritten like this. Let me do this in the interest of space. Write a little less than in the notes, doesn't matter. So, whoa, what did I do here? Let me take a sip of water and give you a second to digest. I made a jump, a jump. But also I'm not going to do any details anyway. But let me give you a second to read at least the jump, and I'll explain the jump. See if you can at least in your minds, or to me, explain the jump, right? This is I. So, and this is, let me just say, this I can say. This is the special function, which is the Airy function. Which are these special functions that you can represent it in many ways, in an asymptotic way, but there's no real closed forms, right, to write it. right? Some of these special functions. So what did I do? If you were to guess, right, what did I do? Let me highlight, because we're getting close to the end, and I'll keep things for next class, maybe do still a little bit of numerical aspects in next class, because I think it's interesting. But I want to finish today with what is the dispersive shock, right? It will be a very good way to finish. So look what I did in words, right? The calculations are not that straightforward, but in words. Just as we did before, I do my Fourier representation. This is omega of k. I substituted here. This was my Fourier mode, okay? And this is the Fourier amplitude. Look, let's double check something here. Maybe, let me put this here. Do I have the right initial condition? Yes, I do. Because at time equal to 0, this is the Fourier transform of the data. So there it is. Agree? Right? Time equal to 0. This at time 0 is the Fourier transform, inverse Fourier transform of the initial data. So I got it. Cool. Right? And did I solve the problem? Yes, because the derivatives are, right? That's how the dispersion relation does. Now, can I write this in a better way in physical space? This is written in Fourier space. Well, then, if one identifies that actually these terms here kind of relate to the special function, the Airy function, and since this is a multiplication of two functions, so this is like the multiplication of the Fourier transform of the Airy function, right? That's the thing that, off the top of my head, if I had never seen this, I would not know. So if I have a multiplication of two Fourier transforms in physical space, this is a convolution, okay? And the convolution rescaled. That's details of the messy calculation. Let's not worry about that. But now it's easy to read the result, right? In Fourier space, the solution in Fourier space is the product of these two Fourier transforms, which means that in physical space, it's this guy convolution with this guy. Here it is, this guy convolution with this guy. Okay? Another interesting fact, too, okay, not so simple to show as I know, is that if we take this guy here, right, that is the Airy function with this factor here, as time goes to 0, look, this guy grows, the Airy function scale shrinks to 0, and it can be shown that this, as time goes to 0, this is like a Dirac mass term. Okay, so it shrinks to 0. It basically recovers this guy, like a Dirac mass. Okay, which is somehow a complicated way of also showing that we sort of recover this guy. Okay, what else I want to say? Okay, I have a little bit of time. I think just more than I need. So we're safe, I think. Safe to have a good closing. So this is, for example, some of these things, not everything, is in Witham's book. So what I'm about to show now is in Witham's book, is that, right, he doesn't show the calculations, but you find some of this in some asymptotics book. I think Ederle is one where you find this. Anyway, so you can show that the Airy function has this asymptotic behavior that I'm going to write just a result. Whoops. Okay, so basically it says the asymptotic. So this complicated looking function, which has this Fourier transform, if you do the asymptotics of this function, as x goes to plus infinity, it has an exponentially decaying front. So this is a near front approximation. And this is shows an oscillatory tail, which means that we can sketch how the Airy function looks like. Okay, so which is like this. We actually have this in, I think, the Airy function in MATLAB. You can do this, or anyway, you could program yourself. It was a long time ago using the expression. So this guy, the near front approximation, tells you this, that this decays exponentially, and the oscillatory tail tells you that basically you have a cosine that decays like this. Okay, which is actually, right, somehow this gives us the dashed line here, to some extent, right? So it's oscillatory. So you see, if you start, and this we do numerically when I do the numerical methods course, if you solve the linear KdV, for example, and you put a Gaussian initial condition at time equals to 0, a Gaussian profile, as time goes on, you see this wave doing this. And this is due to dispersion. The smaller the epsilon, the smaller this tail. Okay? So therefore, if you were to solve, right, I mean, if you were to solve sometimes the KdV without the proper traveling wave, this is what you're going to see. Because nonlinearity and dispersion are not well balanced. Okay? So now, the final thing, great picture I want to show you from the notes. So this is what we conclude then. So that's why I mentioned to you that dispersion generates an oscillatory tail. And you can see, for example, from the dispersion relation of many of these equations, that high frequency terms travel slower. And that's why they lag behind. And that's why you see the oscillatory tail. So if you think of the Fourier content of this initial condition, the lower part of the Fourier modes, which means the long waves, are here. And this is the high frequency component that starts lagging behind. Okay? So now, if we look at the case A, B, and C, from here, maybe the camera should follow me, or, sorry, 1, 2, 3, I'll correct over there, not A, B, C. 1, 2, 3, okay, better to rewrite it over here. So it's not 1, 2, 3, so let me write it as A, B, C. So in terms of a shock, this is what we see. This is the shock. Here we see the viscous shock. And here we see something that looks like this. Let's see the picture I did in the... So this would be the... or we may call it dispersive shock or shock capturing. So what happens, and this is how the comments I will end, is that this is the shock, basically our generalized solution due to Burgers. If you put a small epsilon this way, you get this, and we already saw that as epsilon goes to 0, this transition zone shrinks, and therefore actually one can show, and in Witham you have one way to show this, is that, I don't know if we might show a little bit here in the class, I think so, that as epsilon goes to 0, and here's a sophisticated question that for this guy is more difficult, is that as epsilon goes to 0, in what sense does the solution of B converge to the solution of A? And the answer is it converges in a strong sense, right? Just like this. It converges in a strong sense. Here, the solution of C converges to the solution of A in a weak sense. What does it mean in a weak sense? You have to integrate the solution, because why, let me say qualitative, why does it converge in a weak sense? Is that as epsilon goes to 0, these oscillations here, okay, they become faster and faster, but their amplitude does not decay fast enough to 0. So therefore, you have to sort of integrate. So that if you integrate this, then its contribution zeroes out, let's put it that way. So the convergence of this model to this one is in a weak sense, whereas the conversion of this model is in a strong sense. Okay? So the dispersive shock is more complicated. And let's see what else I want to say. Yeah, this is, I think, it. And next class, I'm still going to begin the class with a little bit of numerics. And I'm going to show you the following. If I try to solve this problem, and I put as initial condition a step, there are numerical methods that might do this, and there are numerical methods that might do this, which means that the numerical method is a diffusive numerical method. It has like some numerical diffusion, just like we saw today that there's some numerical damping. And there's other numerical methods that add dispersion. So it sort of approximates the shock with these oscillations that looks a little bit like a Gibbs effect, but it's basically due to dispersion. Okay? And I'll show you how do you identify that in the numerical method. So it's a good exercise in PDEs, and it will use this trick of borrowing derivatives as I showed you. Anyway, this will be the beginning of next class. There will be a little bit of numerical stuff. Okay? So let's finish here and come back next week.